I will now fill in the details of how this works. So, okay. So the initial state, I suppose, after line 0 is this EPR state on A and B. But then, like, Charlie comes in with this qubit C in this state. So, Charlie made it in the privacy of their own lab, presumably. So the 3-qubit state that we now have is got unentanglement between AB on the one hand and C. Okay, so what I mean to say here is that the initial state, let's say before line 1, over there, is the EPR state for A and B, tensor Charlie's state, x0 plus y1. Okay, and this is like the C qubit. Okay, so let's just expand this out. This is an unnormalized state, but that's okay. So this is 0, 0 plus 1, 1 tensor x0 plus y1. So if we kind of like FOIL this out, if you will, let's see. We get like x on 0, 0, 0. That's this times this. That's first. Next one is outside, so that's plus y times 0, 0, 1. Then inside, so we get like plus x times 1, 1, 0. Plus last is y times 1, 1, 1. Okay, this looks like a bit of a mess, but actually it's not a mess if you draw the picture, the 3-dimensional picture, which we like to draw. So let's do that. So first, after this, making the EPR pair, the picture looks like this. 1, 1. This is EPR. This is 0, 0, 0, 1, 1, 0, 1, 1. This is A is going down and B is going across. Okay, this is the picture of the EPR state, and I'm going to use this convention that like a blank bubble means 0. Okay, so we have like 1 amplitude on 0, 0, 1 amplitude on 1, 1, and no amplitudes on the other two. Now, Charlie's qubit comes in, and the C qubit is going to be like the in-out direction. And basically, we're going to get like x of this on the front face and y of this on the back face. So I'll draw the picture and you'll see what I mean. So let's see if I can do this. Okay. Okay, so that's that. So the front face, this is C, here's 0 and 1. So the front face is like when the C qubit is 0. This is like 0, 0, 0, 0, 0, sorry, 0, 1, 0, 1, 0, 0, and 1, 1, 0. And it's kind of like on the C equals 0 part, we have like EPR times x. Okay, so we just take this picture and times it by x. So we got like x here, blank here, which means 0, x here, and blank here, which is 0. And on the back, that's where like we have 1 in the first coordinate, or in the C coordinate, so 0, 0, 1, 0, 1, 1, 1, 0, 1, and 1, 1, 1. And that's like on the C equals 1 part, we have like y times the EPR pair. So we just have like the same picture times y on the back face. So it's y here and y here. Okay, and hopefully this is the same as this if I got everything right. So I actually prefer to like maybe not ignore this calculation somewhat and just think like, okay, this is the state of A and B, the EPR pair. And when Charlie comes in and has like x amplitude on 0, that's like we get x amount of the EPR on the front face, and we get y amount of EPR on the back face. Okay, so that's like the state here. Now we're going to think about, like, Bob does some operations on B and C. So what are B and C, by the way? B and C are the in-out direction and the left-right direction. So they kind of correspond to, like, the horizontal faces, or like the floor and the ceiling. Okay, Alice's qubit is like the up and down qubit. So it sort of means that, like, Bob has the ability, because he controls B and C, to do like any unitary operation he wants on like a horizontal face, but like it'll just happen equally on the ceiling and the floor. Okay, so he can do any 2 qubit operation he wants. It'll affect the top face and the bottom face in like the same way. Now we're going to figure out what he's going to do, but let's look ahead to step 2. Looking ahead to step 2, like after Bob's done like fiddling around with his qubits, he's going to do extract. And when you do extract, the only qubit that's going to be left is A. And A is in the up and down direction, right? So like there's only going to be like a 1 qubit state A left. And it's going to be like this one, this one, this one, or this one. It's going to be like a vertical edge. And which vertical edge it will be happens with different probabilities. Like if he does some operations and it gets different amplitudes here, then he does extract B and C, then you'll get this vertical edge with probability proportional to the sum of the squares of these amplitudes, and so forth. And Bob is really trying to arrange, actually, so that no matter what outcome he sees, he would really like A's state to look like XY. So Bob's like ultimate dream, which won't quite be reachable, but Bob's ultimate dream would be to like fiddle around with his qubits in such a way that this picture transformed to XY, 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 XY. If he could do that, then he'd be like, great, now I do my extract, and no matter what I get, the resulting 1 qubit state for Alice will be XY, which is the goal. Now it's not going to quite be like that. If he could arrange that, then he wouldn't even need this step 3. But he can almost get that. What we'll see is that Bob's more feasible goal is to just get it so that on every vertical edge there's 1 X and 1 Y. Maybe the X is on top and the Y is on the bottom, or vice versa, that's fine. Or maybe there's like 1 plus or minus X and 1 plus or minus Y. Okay? And that's actually the real thing. So he's going to try to arrange that like on every vertical edge, you have 1 plus or minus X and 1 plus or minus Y. And if he can do that, then when he measures, he'll be like, oh, I measured, and like I saw 0, 1. So I know Alice has this vertical edge. And now this is plus or minus X, this is plus or minus Y. That's almost right. Now I just tell Alice like, oh, you need to swap 0 and 1, and maybe you need to fix up this sign. And that's what's happening here. Okay, so we'll see it properly. But in short, Bob's goal in step 1 is to tinker around so that like every vertical edge has 1 plus or minus X and 1 plus or minus Y. So let's figure out how to do that. And really, there's only so many things Bob can do, right? He has 2 qubits. There's only so many 2 qubit operations. He's just got to like shift these X and Y's around. And yeah, well, let's just do it. And I'll just tell you his actions now because there's only so many possibilities. So, okay, first thing he's going to do is this. If C, then toggle B. And then he's going to do add and diff on C. And that's it. Those are his operations. So like, there's only so many things you can try. This is what works. We'll see why in a second. Okay, so then he, does the extraction. And then he does the transmission. Okay. So let's see what happens here. So I'm going to implement these just by, 1 and 2, by changing this picture. Okay, so what's the first command? If C, then toggle B. So what is if C, then toggle B? If C It's kind of like you check like C's value. You kind of check if you're on the back face or the front face. If you're on the front face, that's where C is 0. You don't do anything. If you're on the back face, that's where C is 1. You toggle B, which is horizontal, which basically means like you swap the horizontal amplitudes on the back face. That's if C then toggle B, like you swap the back edges, the back horizontal edges. Okay, so this Y goes over here. This becomes 0, and this Y goes over here. Okay, that's on the C equals 1 face. We sort of toggle in the B direction, and on the front face, we don't do anything. Okay, and now we do add and diff C. So, okay, that's in the C direction, so that's the in and out direction. And how does add and diff C work? If you remember way back in the day, you go through each of the in and out edges, of which there are 1, 2, 3, 4. And you put the sum of the amplitudes, the add of the amplitudes on the 0 side, and you put the diff of the amplitudes on the 1 side. That's how it works. So on this edge, the add of the two amplitudes is x. That goes on the 0 side. Oh, it's already there. And the diff of the two amplitudes is x, because it's x minus 0. So that goes here. Okay, so here our amplitudes are 0 and 1. The add goes here. That's y. And the diff goes here. 0 minus y is minus y. Okay, so for this horizontal edge, I think it's similar. The add goes here. So that's 0 plus y is y. And the diff goes here. That's 0 minus y is minus y. Yep. And this one's similar too. So the add of x and 0 is x, and the diff is x as well. So it looks like that. And hey, presto, that's exactly what we wanted, right? It's like those two little steps. Now if you look at each vertical edge, it basically looks like you got an x and a y. Okay, sometimes you have a minus y. But you did it, that's it. Okay, so now, let's figure out line 3. So after line 3, so we do extract BC. So as I said, this collapses the state to one of the vertical edges. And this is the BC part. And so Bob's display is just one of these 4 possibilities. And the probabilities are proportional to the sum of the squares of the amplitudes. I say proportional here because we've been using like unnormalized states all along. So you should really first compute the sum of the squares of all the amplitudes and use that as the denominator. But we'll see it doesn't matter. So after line 3, we see the outcome like 0, 0 for BC with probability proportional to, well, this is the 0, 0 edge, so that's x squared and y squared. So x squared plus y squared. And the new state of A is, well, it's just x 0 plus y 1. So in that case, it's perfect. Okay, there's 0, 1. That's minus yx. So with probability proportional to minus y squared plus x squared, the new state for A is minus y plus x. For 1, 0, it's probability proportional to, I think I've written this wrong. 0, 1. Wait, where's 1, 0? Oh yeah, the second one, the coordinates are 1, 0. 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1. Oh, it's this one. Yeah, can't read. Y squared plus x squared. And the new state is y ket 0 plus x ket 1. And the last one is, again, minus y squared plus x squared. And the new state is minus y. Wait, this was x and minus y. And This last one is minus y and x. Okay, maybe I shouldn't have even written it. Okay, but there are two takeaways here. I mean, the main takeaway is that we're basically done because we have basically x and y on each of these. But first of all, let's look at the probabilities proportional to. All these quantities are just x squared plus y squared. Because it doesn't matter what order they're in. This should again be like x squared plus minus y squared. It doesn't matter the order they're in or whether there's plus or minus. Like the sum of the squares is going to be x squared plus y squared. So actually these four circled quantities are all the same. And therefore you don't even have to figure out the constant of proportionality because it's like equal probability. So you can kind of see it's like equal probability 1/4 for each of the four outcomes. And moreover, it's like easy to know what to do for Alice. So finally, from Alice's point of view, when she gets Bob's text message down here in step 4, okay, if she gets the message 0, 0, that's when she knows actually the state's already perfect. So she just does nothing. Let's do this third one next. So if she sees 1, 0, that's when the state that she's now holding has y amplitude on 0 and x amplitude on 1. What should she do? She should do a 1-qubit unitary. Which one? Toggle, yeah. She could just do toggle A. Okay, and that switches it to x on 0 plus y on 1. Okay, if she gets 0, 1, then the state is, if I'm not getting it wrong, it's x amplitude on 0 and negative y amplitude on 1. And here she should do, we didn't talk about this much, but if A, then minus. Okay, so if she does if A, then minus, that leaves this as x, and that switches this to plus y, which is correct. And finally, if she receives the message 1, 1 from Bob, that means she knows her qubit is in the state minus y amplitude on 0, x amplitude on 1. And in this case, what does she do? She does toggle first, and then she does if A, then minus. Okay, by toggling it puts the x here and the minus y here, and then doing this instruction fixes it up. All right, so that's it. That's quantum teleportation. Any questions? Yeah, so actually all this code, if you've been staring at me this whole time, all this code is like depicted on the back of my shirt. But it's in that like awful like circuit diagram notation. So like some of these like, somehow this like, this means like if A then toggle B, and this H is add and diff and so forth and so on. So I'll explain all that stuff to you like later. But yeah, this is how I prefer to think of it. Okay, let's roll the dice. We've been so lucky lately. It's incredible. 2, 1, and 6 chances in a row. I got something new for the prize pantry. I assume we're going to hit it today. Oh, it's off. I think it's hard to do. Okay, we need somebody to watch it. Would you like to watch it? Okay, no practice rolls. Is it okay if I roll on your laptop? Okay. We're going for 6 people. It was a 3. Okay. Well, 3 6s in a row would be very unlucky. Also, it's good that we lost, because next lecture will be very related to those coins that we use for the 1 in 4 chance. So it'll be good to have a non 1 in 6 chance.